Hello everyone, I am Ziwei. I appreciate the opportunity to be with you today. The title of my presentation is Cake Cutting on Graphs, a Discrete and Bounded Proportional Protocols. This paper appeared in SODA 2020, joint work with 贝晓辉、孙晓明、吴浩、张嘉林 and 张志杰. My presentation will be divided in 4 parts. At first, I will introduce the problem. The cake cutting problem. The task of it is dividing a cake into pieces and share them among agents fairly. The problem is a model for fair allocations of resources, and the cake is a metaphor for heterogeneous, divisible resources. Heterogeneous means different agents may value the cake differently, such as in this cake, some people may prefer the chocolate on this cake, and the other people prefer fruit on this cake. And the cake is divisible. It means the cake can be divided into small parts and be shared. Like time and water is divisible. Formally, the cake is represented as interval 0, 1, and a piece of cake, x, is consisted in interval 0, 1. Now I introduce the agent evaluations. We say the set of n agents is big V. We will allocate the cake among big V. Each agent U belongs to big V has a private valuation function Fu defined on the subintervals of 0, 1 with the following properties. Fu much like a cumulative distribution functions. Now we say Fux is the value of x in the agent U's points of view. Fu is non-negative. It means for arbitrary x, Fux is not less than 0. And Fu is normalized. It means Fu 0, 1 is 1. Fu is additive. It means the value of two disjoint pieces of cake is equal to the sum of values of two respective pieces of cake. And Fu is divisible. It means for arbitrary lambda belongs in interval 0, 1, and x, there exists a piece of cake, y, is a subinterval of x, such that Fuy equal to lambda Fux. Now I introduce the query model. Because the valuation functions may be very complex, so we use 2 kinds of queries to access these functions. The first query is evaluate query. The input is 2 points, x and y. It returns Fuxy. The second query is cut query. The input is point x and a value y. The output is point y such that the value of interval xy equal to alpha, and cut this piece of cake out. The complexity of protocols is measured by the total number of queries. Now I introduce the definition of fairness. The definition of allocation is a partition of interval 0, 1 into disjoint pieces with piece xu given to agent u. And there are 2 major fairness notions in the literature. The first one is the proportionality. It means for any agent u, agent u thinks the cake of her at least have the average value of cakes then distributed to everyone. And the second one is unfairness. It means for any agent U, she thinks she had one of the best piece of cake. We know unfairness can imply proportionality. Our goal is find a proportional or unfair allocation. And we will allow partial allocation during the protocol. Partial allocation means there are some unallocated parts don't belong to anyone yet. Now I introduce the cake cutting on social graphs. Assume an undirected social graph G, and the edges in graph G represent acquaintance relationships between agents, like in this picture. There is an edge between agent 1 and 4. So agent 1 can see the value of agent 4's cake, but agent 1 don't know the value of agent 3's cake because there is no edge between agent 1 and 3. So in this situation, the definition of fairness was changed to local proportionality and local unfairness. Local means every agent only care about her neighbors, like local proportionalities means every agent U thinks her cake is not less than the average value of her neighbors. In this big N U is the set of U's neighbors. And the local unfairness means for every age in the graph G, UV, we have FU XU not less than FU XV. We look at this picture. We say agent 1 is local proportional if and only if agent 1 think the value of x1 not less than the average value of x2 and x4. She don't care about agent 3. And agent 1 is local error free if and only if agent 1 thinks the value of x1 not less than x2 and x4. She still don't care about agent 3. Now I introduce the relationship between fairness. Unfairness can imply proportionality. They are local unfairness and proportionality in complete graphs. Local unfairness can imply local proportionality in the same graph. Unfairness can imply local unfairness, but proportional and local proportionality are incomparable, such as in this picture. Agent 1 is proportional because she have 1 in 4 cake, but not local proportional because its neighbor B and D have too much cakes. In this picture, agent 1 is local proportional because the average value of her neighbors is 1 in 5 and she have 1 in 5 too, but she is not proportional. She needs 1 in 4 to be proportional. According to the previous results, we can know finding proportional is easy, but finding unfairness is extremely hard. Finding local proportionality is much harder than proportionality. In this work, they use n factorial queries to find a local proportional allocation in descendant trees. Our work is use 14 to n queries to find a local proportional allocation in any graphs. Our complexity is much better than 6 tower and can deal with any graphs. Now I will introduce our main protocol in general. First, I will introduce the definition of dominant. We say this is a partial allocation, and say big R is the unallocated part. We say agent U is dominant if and only if U remain local proportional, even if her neighbors share the unallocated part. We can see this picture. We say agent A is dominant if and only if we add the value of an unallocated part to A's neighbor B and D. Here, and A is still local proportional in this definition. At this time, we say agent A is dominant. Dominant agents can leave the game safely because we can only allocate the unallocated part to the undominant agents, and the entire situation keep local proportionality. Our protocol have two properties. The first one is when we allocate the cake partially, we keep local proportional manner. And second one is we will repeat some operate many times to shrink the unallocated part. During our protocol, we managed to make agents dominant one by one. In stage 1, we will create the first dominant agent, and in stage 2, starting from the first dominant agent, we will make every other agent dominant. Stage 2 is much simpler than stage 1. After all of the agents dominant, if there still remains an unallocated part, we can allocate it arbitrarily by the definition of dominant. We have a tool, the core protocol. In our main protocol, we will call this core protocol too many times. The input is the core protocol's input, including a big R. means the piece of cake to be allocated, and a big N is the subset of big V. E is the set of agents to allocate big R. R belongs to big N is the cutter. And the core protocol will output an allocation, and free allocation among agents in big N. This allocation may be partial, and a new unallocated part of R prime. Let's be like this picture. Before the core protocol is entire piece of cake, and after the core protocol, it was divided in the allocation and the unallocated part. It and the mechanism prove the core uses at most this number queries. We prove that the core uses big O C2N queries for any C larger than 4. Core protocol have some properties, like cut R obtain 1 in M cake. Here M is the norm of big N, and the unallocated part satisfy this formula. This means after the core protocol, the unallocated part will scale down, and the returned allocation contains an insignificant piece XU. We say XU is insignificant piece if and only if FRXR minus FRXU not less than this value. We think this value is big enough. Now we can see if cut R's neighbor U holds an insignificant piece, R will be dominant after running core another big O n log n times. Why? First, R's piece is much larger than U's. Since XU is insignificant, how much larger? As much as this value. And the value of unallocated part decreases exponentially when running core on and on. So if we running core so many times, the unallocated parts the value of unallocated parts will smaller than this value. At this situation, we can give the whole unallocated part to agent U, and the agent R may keep local proportional. This is the definition of R is dominant at this time. At this time, we can say R is dominant. Now I will introduce the main protocol in details. In stage 1, we will create the first dominant agent. At first, we will run core enough number of times, say big C prime times, and maybe some neighbor of U of the cutters gets the insignificant piece. And now we know R will be dominant by running core so many times, by shrink the unallocated part. Otherwise, then there must be some non-neighbor U receive insignificant pieces in big C allocations. Then we will find a shortest path from U to R, and change the insignificant pieces from U to U1 and to U2 until U2 is a neighbor of R. Then R can be dominant by shrink the unallocated part. The point of this protocol is how to keep local proportional in exchanging the pieces. Let's see this situation. If U and V exchange their pieces in U's viewpoint, before the exchange, the value of U's cake is C, and the value of V's cake is C minus B1. After the exchange, the two pieces of cake exchange. And now we calculate the U's total loss with respect to her neighbors. It means the sum of values of U's neighbor's cake minus the value of U's cake times the number of U's neighbors. And we see U's total loss is non-positive if and only if U is local proportional. And we can see this value can be positive. So we cannot exchange the pieces directly, since we need to keep local proportional. We can solve it by pick a subset of allocation to exchange pieces. Assume there are 4 allocations generated by core. This is the first allocation, the second allocation. And in the first allocation, the value of use cake is C1, and the value of with cake is C1 minus B1. And we say B1 is not less than B2, then B3 and B4. If we only change C4 and C4 minus B4, then use loss in first allocation, at most 3 B4, will be covered by B1 plus B2 plus B3. This comes from the first 3 allocation. In the first allocation, the loss must be less than minus B1. And in second allocation, the loss must be less than minus B2, and this must be less than minus B3. When we add the 4 loss together, the total loss must be non-negative because of this formula. So at this time, we can see the overall allocation is local proportional. Similarly, if there are du plus dv plus 1 allocations returned by core, we say du is the degree of u. And we can ask u keeps du allocations where her value minus width is largest. And ask v keeps dv allocations where her value minus use is largest. And only in the last allocation, exchange pieces between u and v. At this time, we can see the overall allocation remains local proportional. So in this picture, as first, there are big C allocations. Now, all the insignificant pieces is held by agent U. And in each exchange, only a small part of allocations, the piece of the cake is exchanged. So in here, only big C3 allocations, agent U3 holds the insignificant pieces. Big C3 is much less than C, but we only one insignificant piece in U3 can make agent R dominant. At this time, we make the first dominant agent. In stage 2, we will make other agents dominant. Stage 2 will run in n-1 rows. In each row, a neighbor of dominant agents is picked, and the neighbor will be dominant after this row. Like we first pick this agent. After the first row is become dominant, and then we pick this agent. It's a number of dominant agents, and after second rows is dominant. What happened in each row? In each row, we note big D is the set of dominant agents, and U is the neighbor of big D. We run core big O n times. The point is the core protocol don't allocate the cake to dominant agents. So U in the the use point viewpoint, U gets a lot of cake, but we get nothing. It's just like we get an insignificant piece. So U can be dominant by shrink the cake. Conclusion. It is known local proportional can be found using big O 14 to n queries. And there are lots of things remains unknown. Like the lower bound for the local proportional, can it be big omega n log n is the lower bound of unfreeness. And can local proportionality be found using polynomial queries, or can local proportionality on directed graphs be found using single exponential queries? Because our result is on the undirected graphs. Thank you. Any questions?
Okay, thanks, Wei. So we got questions from the audience. And the first one is the query complexity reallocation algorithm tight? And what is the best non-trivial lower bound now? And what is the lower bound you guess is tight?
The best non-trivial lower bound is unlog. We try to find a better lower bound, but we don't find it. I guess we try to prove it have a big omega n2 lower bound, but we failed. Yes. Okay, thank you.
Okay, so yeah, I can ask a question actually. Can you provide a real-world example for this cake cutting on graph? I understand the setting, but can you give me some, like, we really want to do that in practice?
Okay, I say like there is short city, and they want to share water, and the water is a resource and don't have too much water. They all four cities want to have water.
I see.
And each cities have a very big distance. So the people in city A don't know the situation about city D.
I see.
Okay. So now we want to share the water fairly. Make the people in each city don't envy others. Like maybe the people in city A can see the people in city B and C have too much water than he, or then he will envy.
I see. Yeah, I think I get it. Okay. So my another question is like, it seems like this complexity queries is like large, and I know you already changed your research interest to quantum computation.
Yes.
I think it's possible like quantum can help in this case.
Quantum help in this case. I think maybe it's not easy quantum to help in this case because the basic operator in this case is query. How to use quantum to make this query? Because cut a cake is operate, but not just computing.
Okay.
I don't have some idea.
Okay.